but we also we included a new not included, but we talked about the possibility of the loop antennas being put together on top of each other or in a form of an array. In case we have, let's say, a single turn of a loop antenna, which is like a circular path, we expect a resistance which is given by this expression, which is 20 pi square times the circumference divided by the wavelength to the power 4. Now, the circumference of the loop antennas, we often are going to define them in terms of the wavelength, especially when we determine what type of regimes we are dealing with. And so we are going to see this expression, the first equation on the slide again. But at the same time, we have also the option that we can use several turns for a loop antenna, and in that case, the resistance it is going to be proportional to the n square, which, as we talked the last time, it's also something good. So the resistance might increase a lot, but it might be good from one perspective, so that by changing the number of loops, we can match it with the impedance of the transmission line, which is bringing the wave, the electromagnetic wave or signal from the generator. Now, we have some factors which we can put the loop antennas on top of each other so that we can have a possibility to match the impedance of the transmission line. But this one adds to the problem a new resistance, which is called the ohmic resistance due to the proximity. So this proximity, it is strongly related to parameters such as C, where C now is a distance between the two loops. So two loops that can be put at some distance, and also B. B, it is the radius of the wire, and this is not a small b, okay? It is not negligible. You might assume for practical reasons something from a 1 centimeter to 10 centimeters. So it is not something that can be neglected. Now, the effect of all of these loop antennas and having several loop antennas merged together, this brings to the problem the ohmic effects or the resistances associated with the antenna. Now here we see the ratio of the ohmic resistance due to the proximity, found the ratio with respect to the resistance where the proximity effect is neglected. We notice that more loops we have, we see that a factor of 2.5, or at least we get twice the original resistance if we neglect the proximity effects. So if we have a transmission line which is bringing in a signal with an input impedance of 200 ohms, then if we don't consider the loops, the R0, it might, so we might be lose, let's say 50% of the, not 50%, we might have a mismatch of around 50% between the input impedance and the impedance that we want at the antenna, just because we might not be considering the proximity effect or the changes that are caused in the resistance because of this new effect. Now, the electric fields that, wait a second, so we analyze these types of antennas, the electric fields that can be generated in the near field regime, where Kr is much smaller than 1, and Kr is 2 pi over lambda, so the R can be described as a function of the wavelength is 2. So if this is 2 pi over lambda, that means that R is going to be something like 0.1 of the wavelength, or let's say 1% to 10% of the wavelength. This is going to be considered the near field regime. And this is how the electric field is going to change. One thing that you might try to remember whenever we are analyzing the behavior of the antennas is we should remember the behavior of the electric field component. The magnetic field component is going to be related to this, but it's a good reference to remember, for example, that E, it has a direction of E phi for a loop antenna, based on also on the symmetry, and it is changing as a function of sine theta, okay? So often you might remember this. If you don't remember, you can always go back to the derivations of the loop antennas, but remembering that this sine theta is a good reference point because you can immediately relate to the power density, which is going to look like sine square theta. If it is like sine square theta, you get a feeling of how the distribution of what the directivity of the antenna is going to be. Now, this was a near field, this would be the far field, and the E phi, if we have a look at E phi, we don't have, wait a second, 4 pi. So in the far field, the one major difference is the rate of change, how the electric field is changing as a function of distance r. In the near field, we observe that the E phi component, it is decreasing very fast, at a very fast rate. It's 1 over r squared. But in the far field, it is just changing as 1 over r. A similar behavior is also observed for the magnetic field intensities for HR and H theta, which are the direction of the fields orthogonal to E phi. Okay, so we said before that the electric field intensity might be changing as sine theta. That's okay, and the power density is changing like sine square theta, and from here we can find the directivity. For a small loop, this is what we find. If we have now, we are assuming, let's say, an antenna that has a radius of, how can we denote this one? 4% of a wavelength that it is transmitting. So 4% is 1 over 25, and the surface area that we need to calculate is pi a squared. And once we substitute these respective values, we can find what is the effective area of a specific antenna. And as we can see from here, the effective area of the antenna is something lambda squared times 0.1. Now, all of these antennas, since we said that we can adjust those regarding the impedance of, we can adjust the impedance of the antenna, which has an intrinsic resistance, and some resistances that come because of the proximity levels, we have to analyze this with regard to some equivalent circuit to match it with the transmission line. Now, the equivalent circuit is going to look something like this, but in this circuit, we may use a capacitor CR in order to, in parallel, so that we can resonate with the antenna. Now, we'll see a couple of words regarding that. Let's have a look of these regarding these major components. For the input impedance of into the antenna. So we see the input impedance, it has some radiation resistance, it has also some inductive reactance. Now, a loop antenna, it always has some inductive reactance, okay? This is what happens with loops. Without even, you don't need to have some effective in L or effective capacitance attached to the system. So we just need to include here the omega LA, where omega is going to be the frequency associated to the wave transmitted from the generator. Okay, so this is going to be the circuit equivalent. Now this CR, we can use this as a mathematical tool how to obtain a resonance of the antenna, because we said that the reactance from the generator for loop antenna, traditionally this behaves like L. We can include also the C, so that we can try to get the resonance, and we do all remember that the L and the C, they have a different effect with regard to the phase shift of a wave which is coming through a specific circuit component. One allows the current to lead the applied voltage, the other allows the voltage to lead the current. Okay, so these phase differences between C and L allow one to have a perfect match such that the phase difference between the current and the voltage can be zero if we achieve the perfect match between the values of C and the L. Now, these are the values for the input resistance and the input reactance. And all of these input resistance and reactance, this can be assumed like the total impedance of the system. And this is we can try to determine what is the value of the capacitance in order to eliminate the complete. So if we have a look here, if we want to eliminate the BI, this means that we are at a resonance, or the effective time delay or time shift is going to be equal to 0, since the complex component, the B, which is described separately in 534, B, that one it's just a component of the equation 5.34. So we want to zero the B input. At resonances, this is what you observe for the input impedance for a specific component, specific antenna. Now this inductance, which is always there, so let's call it this way. It's a loop antenna, so it's always there, okay? It doesn't have a direct capacitance, but L, it does have it. And this one, it can be calculated for a loop as given in the equation 5.37. So we see that there's a permeability function, there's a radius of the wire A. It's also, it also depends on the wire radius B. And if you remember, often the capacitance and the inductance for different geometrical systems, these values often they depend on the geometric factors or geometric aspects of the components. One reason for this is that at least for a moment, if we just try to relate to the inductors and the capacitors that we have dealt so far, not from the perspective of the antennas. If you remember, in capacitors and the inductors, there is always some energy which is stored. The energy which is stored, it is going to be proportional to the currents and these parameters, and we can find the energy density. Now, the energy density, it is joule per meter cube, but to find the total energy stored, we always multiply with some volumes which can be associated to the antennas. So that's why we get an intuitive reminder that these components will be directly depend on the geometry of the system. Geometry of the system, it relates the radius, circumference, surface area, and also the wire radius. And it's not always a wire, but we can clarify this one. These loop antennas, they are not always a wire, but you can call them just a conductor. Okay, you can pick up a conductor. It doesn't. You make it in the form of a loop. There you have it. Now there is a similarity between if we have a circular loop and a square loop, and but the equations they also have a slight difference, which is seen in the last term of equation 5.37. Let me see just for a second. Is there any comment regarding present? Okay, so these are the equations that you can all find from the textbook. It is, I'm trying to find it, it's just the first, it's on page 274, and all of these relations, they're considerably useful whenever we solve any equation because they are hard to remember. Okay, loop antennas, they can be used as receiving antennas or probes to measure magnetic flux density. So when a plane wave impinges onto a loop antenna, an open circuit voltage will develop across the terminals. So we have seen this one in dipole antennas before, where the antennas, they had that form, they were linear. Once there was an incident electric field on top of that, multiply the electric field component with the effective length of the antenna, we used to find an open circuit voltage. So there will be without an external power supplier, there will be a voltage difference across the ends. Okay, so this is what it says develops across its terminals. Now, in order to analyze this one, we, in this case, we have the loop antenna lying on the XY plane, and we determine a plane of incidence, which is a plane formed by the Z-axis and the radial vector. So in this figure, you can, it's going to be the Z-axis and this point where the electric field and the magnetic field intensity are shown. Okay, so with respect to this plane, we assume that the incident magnetic field intensity vector, which is the HI shown in this slide, it creates an angle psi with respect to the plane. Okay, so at the plane, this lifts by this much, and this value of the open circuit voltage VOC, it is given by this expression here, which is j omega pi a square times BIZ. And we see that pi I squared, this would be the surface, the complete area of the antenna. And this component, the VOC, it can also be represented as both as a function of h and as a function of e. Assuming that we are going to, if you see equation 5.539a, there's a difference, but it can be expressed as a function of both of those. Now, so again, this is the Thevenin equivalent of receiving loop, and this VOC that we found here in this slide, this can always be written as an effective length scale of the antenna times the incident electric field value. Now, this effective length scale, let me see this. Okay. Now, here we have an argument that in the effective length scale, we have a factor which is a cosine sine theta I, because initially, when we defined the VOC, we were considering the VOC to be proportional to the BZ, and BZI, which is the incident magnetic flux density. Now let's notice for a moment here. Okay, now for a moment, we forget that we're dealing with a very small loop, but we assume a large loop, or a loop which does not have to be, we don't need to approximate anything. And with this regard, we need to calculate the vector A, which is shown here in this slide. So we always try to determine this. The issue then comes trying to determine what is the denominator and the numerator, which these factors then help us to determine what type of approximations we are going to use. Now we can move here faster, and this expression, which was shown a couple of slides before, for the magnetic vector field, which is the A, this is what it's going to be. But now, regarding for far field observations, we are going to have two important terms which we have to consider. One is R, which deals only with regard to the amplitude, but we have also another term which is for the phase. Now the phase, it is strongly dependent, I mean to some degree, it strongly depends on the angle theta and on the angle phi. So that's what we have to include. If you notice carefully, the 1 over r, which is a capital R, it is substituted with a small r, which is for amplitude terms. But to check for the phase, how much the wave is oscillating, for the e to the power jka, we substitute the whole r minus a sine theta cosine phi. And also, this the small r, we can take it out of the integral, because it just depends on r, and the integral over which we need to calculate the a, it does not include any r, it's just integral over the angle phi. And the major reason for this is that, so let's not forget why we are integrating over the phi. We should integrate over the phi because the loop antenna is on a plane, something like in here, and the direction of the current, it is along the phi. So I is equal to I0 times A phi. If you remember, in dipole antennas, the current was most of the time along the z-axis. So it was a wire pointing along the z. If the wire is pointing along the z, also the A, the vector potential A, is also AZ. Okay. Now, if the current is A phi, the A phi will also have the same direction as the current. Okay. So let's try to remember again why this integral looks this way. Now, let's move a little faster. So we have here the A phi, and then A phi here, we just do a trick here. We are integrating from 0 to 2 pi, the complete angle phi, but since we want to use some symmetries with the Bessel integrals, we're just separating the integral from 0 to pi from 0 to 2 pi, we separated from 0 to pi and from pi to 2 pi. And once we do that, using some symmetries, we can write this one as the vector A, it is going to be equal to the integral of a couple of terms, which is then equal to pi j times Bezier functions of the first order, and the function x is ka sine theta. Now, here we have the description of how this integral can be related to, and the Bezier function. I'm going to say a couple of words regarding these. I mean, this seems like some really good math that we may need to have a look at those. Now, since if we consider the Bezier functions of the 0th order, we can substitute. Let me see. So here we just write the Bezier function of first kind. The moment the Bezier function is denoted by j, this would be a Bezier function of the second kind. We have some Bezier function of the second kind if we use the y. Let me see. We don't. Okay, so let's move back here. Here we just have the symmetries of these functions. I'm going to give some relevant aspects which can become useful to you not only in antenna course or in courses related to antenna, but also more general other aspects. For a moment, let's remember once again that we had a current which was pointing along the A phi. For that reason, the vector potential A has also a direction along the A phi. We described the A phi as a combination of Bezier functions J's, which are shown in here. And then finally, we obtain, so we using this interesting property of the Ji's, we just add them together, and you can notice this effect into the second line, which gives the A phi, and the fourth line. So we are dividing by 4r in the second line, and then we divide by 2r in the fourth line, just because the j and minus j, they are equal to each other when Ka is substituted with minus Ka. Now this Ka, it is in fact a phase term, a shnushim phase, and let's think about it. It is a phase term because it appears in the exponential to the power jkx, right? So we never forget that. And the unit of this one, it is radians. K is 2 pi over meter. A is meters, so 2 pi over meters times meters. The meters cancel out. We're left with the phase difference, or with radians. Now, we found the A, which apparently A is going to be a Bezier function. But we have to remember that this is for the far field. Then we should remember from a few sections ahead that the E field and the H field, so the electric field intensity and the magnetic field intensity, they do relate with respect to the A component as shown here at the equations at the bottom. So since A theta is equal to 0, we get also that E theta is 0. Since A phi is different from 0, given by equation 5.53, we can also determine the E phi, and E phi, it's going to be the same expression like 5.53 divided by the j omega. Once we divide by j omega, we find electric field, which is not a complex term, okay? It is not purely a complex number, and this is something to notice. And the same way, we also observe, because actually A, let's not forget, in far field regime, it's a purely complex number. Okay, but then we find that the field intensities, they are not complex numbers anymore. And let's see. Yeah, so the top right side of the slide is also an important conclusion with regard to what we are doing so far. And we notice that we have a wave that has a component E phi, and another component is along the H theta. And now the cross product between these two, it will give the power. So here again, we have the only non-zero terms of the electric and magnetic field intensity. There are two terms which are shown here. Now here we have the Bezier function, which in the near field, it can be approximated as x over 2. okay? Because this is Bezier function. And again, we see a Bezier function, which is a summation of different ordered polynomials, okay? Which means that this should not be very challenging. This should be relatively easy because polynomials are easy to work with. Now, here personally, I find something important aspect to notice is that the Bezier function, they do look like, or they do have behavior which looks like almost oscillatory function, but it is not like sine or cosine. Okay, so I've had some I've had some challenges to try to fit some data for some complex systems. And these complex systems, they were obtained from the solution of differential equations. So let me repeat what I said before a while. I had a problem where I had some data points which had an almost oscillatory solution, and those points did obey a differential equation, and a traditional approach could be that we have an oscillatory behavior of some factors as a function of time. But now that we know how the Bezier functions behave, we can also say, or some of you might see these in other topics. I know you have taken numerical analysis before. Over there, you have the solution of differential equations. Oscillatory solution, once you see, you can option or you can consider assuming the solution to be like a Bezier function, but this often happens only after you have seen how a Bezier function looks like. Okay, I know that everybody is lucky enough to see Bezier functions in the early stages or the mid stage of the bachelor study program. Now, again, here we kind of saw these slides, only that, not these slides, these equations, only that we have not substituted the complete expression for the A phi. Okay. So these are the electric field intensities and the magnetic field intensity. Once we find these, we notice that there are only two components, one E phi, one H theta. We take the cross product with the complex conjugate of the magnetic field intensity. We find the power density. The power density multiplied by R squared, we get the radiation intensity. And finally, we can also find the total radiated power, which is equal to the radiation density, integrating it over a closed surface. And this closed surface, you can clearly see that we will be integrating over some constant radius. Okay, so we'll integrate over phi, d phi, and d theta. The integral of d phi, it is clear from 5.57 to 5.58 because there is an extra term of 2 pi. So you see in 5.58 we have a term of pi, and there is also a 2 because that's what happens if we integrate d phi over 2 phi. And then the rest of the integral, it includes sine theta d theta, which is traditionally the volume element. Now, in case we have a loop antenna which has a radiation intensity which has some Bezier function in it, the distribution is going to look like this. Now, we do observe the Bezier functions, or we feel the need for using these functions in this case because we are dealing with a circular loop, but we're not doing much approximations. We're not assuming that the loop is very, very small. But now the radiation intensity, it strongly depends on the value of the circumference of the loop antenna. If the circumference of the loop antenna is 10% of the wavelength, this is the distribution. If the circumference of the antenna is not 10%, but 500% of the wavelength, this is what we observe. We're seeing 500% because the circumference is equal to 5 times lambda. Okay. So, wait a second. So this is just the distribution. We came back again to the equations that we saw before a while. They are not different at all. So just 5.57. We saw them here. These are also shown here again. And so J1 is the Bezier function of order 1. we did remember this. Here we have the radiated power, which is equal to the integral of the Bezier function square. And by the way, this is what we should get, because the electric field intensity itself, it was a Bezier function, not square, but to the power 1. Radiated power, it is proportional to the electric field intensity square. Okay, now this integral that we see here in this slide, now this is just purely mathematics, and probably from now on we'll try to skip a little faster. But let's try to understand the approach that is commonly used. So here we see that the radiated power is J square integrating over the theta. And if we do a change of variables, we can say that this integral, which is equal to the integral from 0 to pi, this can be approximated by using a a Bezier function of order 2. It is of the first kind, but it is of order 2 because we see the J2. Now the equation 5.59, this equation that we see here, can be cast into the form, can be described as we see here at the bottom. So the Bezier function, let's assume for a moment, Bezier function of first order is like a polynomial of first order. Now we have the Bezier function of second order because we see J2. And so J1 square, it is proportional to J2 because it's like x and the x square. Now this Ka sine theta, you can consider this one as u. Pra quhen e sikur uja është barabartë Ka her sinus theta. Nëse uja është Ka sinus theta, sa është d uja? D uja është Ka që shëmzon cosinus theta. Dhe del pastaj d theta. Pra që do të thotë ne mund të marrim të pjesën e në krah të djathtë të ekuacionit të parë. Tani bazuar në aparat matematikor i cili shpjegohet në referencat 16 deri në 20 të librit jon, nuk e di ai gjë do të thonë. Duke se nuk i kam. Jo, si kam këtu. Referencat 16 deri në 20 të librit ton. Ne mund të gjejmë for the m. Kemi faktor që njësh. For the moment, we're just trying to see how these integrals play out in a specific domain. For example, when we say specific domain, we're talking about the large possible loops, as in this case. So this is, we're still trying to find the radiated power. The radiated power for large loops, let's see for a moment, it looks like they are proportional to the 1 over Ka. So this is what we observe. This is something odd, not very odd, but we notice that the integral of the Bezier function of the first kind, first order, it is 1 inverse radians, okay, because Ka, it is equal to radian, so it's a phase difference, and this is inverse phase to some degree. Actually inverse phase doesn't mean much because radian, it is really no unit. Inverse radian, I don't know how I can represent it differently, but let's move ahead. So if this is the case for the integral, then the total radiated power is given by equation 5.61. Pra tek 5.60 kemi zëvendësuar integralin i cili del 1/2 Ka. Tani, the maximum radiation intensity, U max, occurs at a specific value. Wait a second. Yes. Because the U max, it is proportional to the Bezier function square, and the Bezier function square, we can see this. Wait a second. we have here large loops. After large loops, we have some relevant approximations for the radiation resistance, which is the first equation here. Once we know the radiation resistance, actually, we can also determine the directivity, and directivity is always a ratio of maximum radiation intensity to the total radiated power, and we find the expression shown over there. Now, here we have the second case where large loops, this would be the intermediate loops, trying to determine what is radiated power, but now for loops which are not large. They are something smaller than half a wavelength and larger than 5% of the wavelength. So maybe we can call it like this. Between 5% of the wavelength and 50%, these are the equations that we observe. Why do we call it 5%? Because 6 times 3 is equal to 18, around 20. 1 divided by 20, it is 5%. 1 divided by 2, it is 50%. So in this regime, we have these relationships or this expression for the total radiated power. Now we go for loop antennas, which are less than 5%, okay? So anything which is between 1% and 2% with respect to the wavelength, which is emitted or transmitted by the antenna, we have the equations which can be given by the small loop. And here we really do have larger simplifications or approximations. Okay, so we have a small loop here, directivity, effective aperture, they are given by the equation shown in here. Now here we have some summary in a couple of slides, then we move ahead and do some more, or we can talk some more regarding the different types of loop antennas. Now if you like, we can have a short break here.